let's have a look. Where is it? Let's find the file. Still forgot to say something. Doesn't matter. We can look at it here. Right. This is exactly the same data in SPSS. Now, the thing that I forgot to say about before is these test tubes which have nothing in. So they had nothing in to demonstrate that if there's no substrate in there, the enzyme doesn't do anything, so its rate should be 0. But 1/0 is not 0. It's infinity, and so these two things should both be infinities, and it's all a mess. So you need to ignore those particular rows in doing your calculations. So the first thing you need to do is pop into variable view and add some missing values for the inverse 1/s and 1/v. So we need to put missing values of 0 in there so that we don't have any problems. Good. Now we've got our data set in the appropriate state to do some kind of analysis. Now we can do exactly the same sort of graphical methods that we did before. Now the other thing that I've added here is a column which says inhibitor or not. So I've used inhibitor as a categorical variable. 0 meaning there isn't there, and any inhibitor, 1 meaning there is. So what I want to do is a scatter plot. I'm going to do one of these which has group scatter, so it has multiple colors, because I've got two different groups within my charts that I want to consider. So which way around do you draw your graphs? Which one is the dependent variable and which one's the independent variable? So which thing is causing the other thing to happen? Is my velocity cause 1/, my 1/, velocity causing my 1/, substrate to change? Or is my 1/, substrate causing the 1/, velocity to change? So the 1/, substrate, that's your independent variable, your explanatory variable. As I change the substrate amount, it changed the, yes, so 1/v is the dependent. That goes on the x-axis, and I'm going to set my color based on inhibitor. Okay, I press OK. And I end up with what you can hopefully see are two distinct lines. But to be honest, because of that outlier, it's very tempting to fit two very closely parallel lines to one another and not fit this lower line down here. You can get yourself in a right mess here. So you've got that graph. I can now select that graph and I can go here. And what I can do is I can add a total trend line, which would merge both sets of points together and put one line of best fit through the middle of them. That's not really a good idea because we know they're two different lines. And there's this second one which adds a fit line at the different subgroups. So if I click on that, it'll add two separate lines. That's perfectly fine and exactly what I want. So I've now got the lines, and it says y equals 76.92 plus 8.99 times x. I should have left my other one open, my Excel one open, so that we can sit there and go to this. So the uninhibited 76.92, 8.99 x. So I'm getting exactly the same numbers. And then if you look at the other one, the red one, that is 1.66 times e to the 2, so it's 166 plus 32.67x. And if I go back to the other one, it's 165.59, so 166 plus 32.66. So it's exactly the same thing. You can extend the line weaver back to the negative, but you don't really, well, first thing, that's an extrapolation and not really good idea. But the key things the line weaver back plot are the gradient and the intercept. And in a minute, you'll see why you shouldn't use a line weaver back plot, because you'll see why. The results of it are not very good. So here, I've got exactly the same kind of result as I get out of Excel. I've got no diagnostics. I've got no proper analysis as to what's going on. So what I need to do then is I need to go back and do the proper linear regression. So I go to Analyze, go down to Regression. There's lots and lots of different types of regression. Let's stick with linear. You can do curve estimation, so fitting a curve to the Michaelis-Menten if you wanted. That would work as well. So let's click on linear. So what I want, my dependent variable we've established is going to be 1 over v. My independent variable is 1 over s. Now in this case, I've got another thing that I want to do, which is the selection variable, because I want to fit two separate models. So in this case, first I'm going to fit the uninhibited one. Continue. The other thing I want to do is I want to put confidence intervals on the slope and the intercept. So you have to click on statistics and then click on confidence intervals. Press continue. The other thing that I want to do is I want to look at some diagnostics. I want to see whether the lines are a good fit or not. So I'm going to calculate a thing called the residuals. Now, what SPSS will do is when I run this calculation, is it will add an extra column to my output, which contains the residuals. So I click on the save button because it's going to save some new columns. I'm going to calculate both the standardized and unstandardized residuals. So unstandardized will give you the actual number, the difference between the line, where the line predicts the value of y should be for that value of x, and where your actual value of y is. So that will give me the height here and the height here. Whereas if I standardize it, it will move the differences between all of them to have a mean of 0 and a standard deviation of 1. This is useful because if I look at it and go, anything that's above 2 standard deviations away from the mean is unusual. So that's likely to be an outlier. So looking at the standardized one is very much quicker and easier to detect when there's an outlier compared to looking at the unstandardized ones. You can look at the standardized ones and get the same thing, but you need to know what the standard deviation is for your residuals. SPSS does tell you, but the other ones are a bit easier to look at. Press continue. Inhibitor, everything done, press OK. So now we get the output of a linear regression model in SPSS. The thing about it is you're used to looking in Excel, so you're used to looking at this graphical thing. But when SPSS does it, the true regression thing, it doesn't give you a nice picture. You can create the nice picture, but it doesn't give you one. So the first thing it tells you is how you constructed the model. In this case, there was only one independent variable. You can have models where you have multiple independent variables. That's called multivariate linear regression. It tells you the R value and it tells you the R squared value. Notice it does it for the two different groups. So this is for the one with no inhibitor. This is one for inhibitor. It's not very helpful to do both of them, but it does it anyway. The next thing below that is called an ANOVA table. Don't hugely worry about this at the minute. The only two things that you need to look at is this F and this sig. This sig must be below 0.05 to tell you that you have a realistic regression model, that the model is a good fit to your data. It's 0.108, that's bad news. It's telling you your regression is not very good. Now, if you did this in Excel, it's giving you no kind of warning that your regression might be a complete pile of mess and disaster and not to be used. Now, if you go down to the next, you have the actual model. So the way that it writes, the SPSS writes it, remember I said a line is defined by two things, a slope and a constant, the intercept. So it's easy to read from the table what the constant is. So you go to the column that's headed with B, which actually stands for beta, because the way they write their equation is not y equals mx plus c or y equals a plus bx, or however they write it, y equals beta 0, which is the constant, plus beta 1x. Then if you add x squared, it'd be beta 2x squared, and so on. So this one is your beta 0 and it's your constant. So it says it's 76.924. We've seen that before in the Excel one. That's all good. And then below it is the slope. So the slope will be in the row which starts with whatever the name of your x variable is. So in this case, we put 1 over s to be the x variable. So the slope is 8.986. That's exactly what we saw on fitting the line to the graph. But if you look along from here, so it's calculate, there's some more sig values here that you should look at. So the sig value for the constant is awful, just terrible, nowhere near 0.05. For the gradient is closer to 0.05, and it's exactly the same number as the sig from the ANOVA table, and this will always be true. The lowest value of the significances in this coefficients table will be the value of the F statistic in the ANOVA table, because it's the same thing. Next, it has what's called the confidence bound for your constant, if you read that row, and for your gradient. So it's saying the constant can be anywhere between minus 793 and 947. So basically pick a number and you'll be right. It's saying that the slope can be anywhere between minus 2.821 and plus 20.793. So it can be a negative downward slope as you increase the substrate concentration, the velocity goes down. I don't think that's possible. Or it could be a massively positive slope with a gradient of 21 compared to 9. If this confidence interval contains a change from a negative slope to a positive slope, then it contains a zero slope. That's one of the possibilities in the confidence interval. And zero slope would mean that you can change your value of x as much as you like, y remains the same. That would be telling you that regression is not possible. So from this diagnostic, I can immediately tell that I've got something horrible going on with my data, and I cannot use that line fit. It would be totally wrong. If I look at the residuals, notice it's broken into two sections because SPSS, for some crazy reason, calculates the residuals not only for the uninhibited ones, which is what I wanted, but also for the inhibited. So for the inhibited ones, you can see that the mean residual is 997. It's got a minimum of minus 111, a maximum of 3,600. They're just terrible. This is telling you that the line that you fit for the uninhibited is nowhere near the same line that you need to fit for the inhibited, which is good. That's important. If you look at the residuals for the uninhibited, the mean is 0, which is where it should be. The maximum is 1,263. That's massive. And the minimum is minus 530. And the standard deviation is 575. These are all really big numbers and very, very worrying. And you can see clearly on this plot that this one's a bad number. But if I also do the graph of so instead of doing 1 over V against 1 over S, I want to do the plot of the residuals, the residuals that I calculated. So if I do the unstandardized ones to start with and press OK, so what you can see for the red ones, which is the inhibited one, the residuals are always terrible, and they're going up in a straight line. So that's telling you the line is completely wrong. Now the residuals for the no inhibitor, they should be scattered roughly between around 0, with the same amount below 0 as above 0. So you've got one below 0. Most of these are below 0. You've got one which is very strongly above 0 that's counteracting that one. So this is our outlier. And we know it's wrong because it's more than 2 standard deviations above 0. So if you remember, the standard deviation for this was 525. So anything that's bigger than 1050 on the residuals, and this is above 1050, is more than 2 standard deviations away from the mean, and this is an outlier. If I'd have done the graph, as I said, of the standardized ones instead of the unstandardized, then it's a lot easier to read. So here, what you're looking for is any value that's 2 or above. So here is one that's 2. So that outlier is a significant outlier. All those red ones are completely wrong, but that's because it's a different line, and we don't have to actually consider those. We only need to consider the blue ones at this case. So we know that that particular point is an outlier. So what are we going to do about it? So what we're going to do is use missing values again. You see that these extra columns have been added. Every time you run a linear regression model, it will add columns. Now, I don't want to keep these because when I rerun the model again in a second, I'll create some more residuals and standardized residuals. So I'm just going to get rid of those and keep my data set nice and clean. So you can see here that the value that I don't want is the 1 over v, which is 2088. Now, I could ignore all of the values of 1 over v that are bigger than 2000. But if I did that, I'd get rid of these 2 values from the inhibited data. So I don't want to do that. So what I'm going to do is specify a range between 2000 and 2100. I'll get rid of that point, but it won't affect any of the others. Okay, so I go to variable view, I go to inverse v, I decide to put a range, so it'll be 2000 to 2100. I still need to have 0 as a value to ignore as well. So now I've removed that awkward point. This point here will disappear. So now if I go back and I do my analyze and my linear regression, it's saved all the things that I used before. So I've not changed my model at all. I've just marked that one point as a missing value to get rid of and press OK. Now I've got my new regression model built exactly the same way. Now my R squared is 0.991 and my R is 0.997. So I can tell instantly that by getting rid of that single point, I've gone from a model which was not a great fit to one which is a pretty good fit. But most importantly, when I go to the ANOVA table, I've now got an F statistic of 449 and I've got a significance of 0. This is a good model. This is a valid linear model. The other one was not valid. It was completely incorrect. Therefore, SPSS had highlighted this to me and told me I needed to go back and do it again, taking into account my missing and taking into account my outlier, which I've now made a missing value. If I go to the coefficients of the model, the intercept is now minus 11.925. It's still not significant. It's still wrong, and it's still not something that you can use at all. It goes anywhere between minus 72 and plus 48, so it's pretty arbitrary. It might actually go through 0, 0, which would just be unusual but possible. If I look at the gradient now, so it's wrong because the sig value is not less than 0.05. If this significance is never less than, it's not less than 0.05, it's not reliable. Which, to be quite honest, is never going to be reliable because that value, so a value of x of 0, lies outside the range of data that you've collected. So because it lies outside the range of data you've collected, then you cannot use it. So 0.05 is the standard p-value that you have to be below for every statistical test. You can change it to 0.01 if you want to, but 0.05 is the largest possible value that's acceptable for any statistical test. It means there's a 5% chance of that occurring by random. Now this is telling you that the chance of it arising by random is actually 61.3%. So this is almost completely determined as noise from the experiment that you've done. And this is why we don't use Lineweaver-Burke plots, because if you use them to work out your KM, to work out your intercept, they are horribly wrong. Slope-wise, it's fine. So you can work out, I think the slope is Km. So one of the, but you can't work out Vmax. One of the two you can work out perfectly well from Lineweaver-Burke plots. So here we've got the slope is now 6.4, and the confidence interval goes from 5.569 to 7.247. They're both positive, and the confidence intervals are very small range. And 0.000 is a lot less than the 0.05 significance value, which is the threshold for you accepting your model. If I go and look at the residuals, remember they had a standard deviation of 500 and they were in thousands. Now it's -47 to +43, mean of 0. Everything's good. They're still absolutely terrible for the inhibited one, but that's how it's supposed to be, because you need two different lines. Now I'm sure I've got a good fit and a good model, I can write all these up. So I can say that the gradient is somewhere in this range, and I can give it the confidence intervals for it. So that's the confidence intervals, I think, for Km. If you then go back and do analyze, and you do regression and linear regression again, and this time you change the inhibitor rule, so you go from 0 to 1, continue, press OK. This will give you the second line for the inhibited data. You've got a great R squared, 0.993. You've got fantastic F statistic. It is significant because it's less than 0.05. Your constant is still not significant, but it is closer to significant than the other one was. Your 1 over S, so your gradient is 32.67, and it's between 29.627 and 35.707. And if I look at the residuals, the average is 0, and it goes between -201 and +252. I could then plot my residual statistics and do everything else that I want to do. Notice that these are now called residuals 2 because this is the second model. So if you look down, just looking at it from the data, you can see that these residuals are pretty small, the standardized ones here, but they're very big in the second one because this is fitting the line correctly. None of them are above 2. The standardized one, that's fine. All of these are above 2 because this is the uninhibited one, which has a different line fit, whereas in the other one, so in the first model, none of these are above 2 and all of these are way above 2 because there's a different line for uninhibited and inhibited. So the power of SPSS is doing these analytics and being able to tell you, whoa, there's something wrong here, you've got to go back and think about it. The other power of it is giving you the confidence interval, so you're not just saying this is the gradient or this is the intercept, that you actually have confidence intervals for the gradients and intercept. So if you're using that to derive values that you're going to use for something like Km and Vmax, you have confidence intervals for these particular properties that you've just calculated. But the main thing is it's diagnostics. There are no diagnostics in Excel. There are very not complex. There's just a very complete set of diagnostics that you can run when you do it in SPSS, and they're not particularly difficult to access those diagnostics, so that you can know you've done the right regression.